I bought my first 3D printer and for 3 solid days it just sat on my desk collecting dust. I was completely paralyzed. I had this miracle of modern technology, a machine that could literally pull objects out of thin air. And I was terrified to even turn it on. What if I broke it? What if I wasted a whole roll of that expensive plastic filament? What if the one thing I actually managed to print was a completely useless stringy blob of plastic? If that fear, that feeling of being completely overwhelmed by choice and jargon is what's holding you back, then this is the guide I wish I had. We are going to cut through all the noise. We're going to take you from zero, from that feeling of, where do I even start? To confidently holding your first incredible high-quality 3D print in your hands. This isn't just about printing plastic toys. It's about unlocking a superpower. The power to fix, to create, to invent right from your desktop. And let me tell you, there has never been a better time in history to jump in than right now, in 2026. This is the golden age. Just a few years ago, getting a decent 3D printer meant spending thousands of dollars on a complicated kit that you practically needed an engineering degree to assemble. Today, you can get a machine that is light years better, faster, and more reliable for less than the price of a new PlayStation. The technology has matured, the prices have plummeted, and the community has exploded. We've hit the perfect sweet spot where these machines are both incredibly powerful and shockingly affordable. The barrier to entry has been completely obliterated. But before we go any further, we need to bust the 3 biggest myths that stop most people dead in their tracks. Myth number 1. This is too complicated. I'm not an engineer, I can't do CD, I'm just not technical enough. Let me be crystal clear. If you can operate a microwave, you can operate a modern 3D printer. It's become less about engineering and more about artistry and problem solving. You don't need to know how a microwave's magnetron works to heat up your coffee, right? Same principle. The software is now incredibly user-friendly, often just drag and drop. And you don't have to design a single thing yourself to get started. There are entire universes of millions of free pre-made models online, ready for you to download and print today. We're talking about a high-tech hot glue gun, not a space shuttle. Myth number 2. It's way too expensive for just a hobby. This one used to be true, but it's ancient history now. As I said, a top-tier beginner printer in 2026 will cost you between $300 and $500. That's it. But think about the value. That plastic knob on your dishwasher that just broke? The company wants $40 for a tiny replacement piece. You can print a stronger one for about 15 cents. That custom bracket you need to perfectly mount a new shelf in your garage? It doesn't exist. But you can design and print it in a few hours. A perfectly tailored, personalized gift for a friend? The possibilities are endless. This machine doesn't just cost money. It has the potential to save you money and create things that money can't even buy. Pays for itself not just in dollars but in solutions. And that brings us to the most damaging myth of all. Myth number 3. It's only good for printing useless plastic trinkets and little figurines. This is the one that really gets me. It's like saying a computer is only for playing solitaire. Yes, you can print a little Yoda head and you probably will, it's like a rite of passage. But that's just scratching the surface. I'm talking about printing functional, powerful, world-changing things. Custom drone parts. Jigs and tools for your woodworking hobby that make your cuts more precise. A replacement gear for a vintage record player that went out of production in 1982. An ergonomic grip for a video game controller that perfectly fits your hands. Organizers for your workshop that are designed specifically for your tools. We are talking about turning your ideas into physical reality. It's a machine for problem solvers. It's a tool that empowers you to look at the world and say, I can make that better. So what exactly is 3D printing? Forget all the technical jargon. Here's the simplest way to think about it. Imagine you're building something, anything, but instead of starting with a block of wood and carving away everything you don't want, you start with nothing. And you build your object up from the ground, one microscopic layer at a time. Picture a robotic nozzle like a tiny, incredibly precise hot glue gun, drawing the first layer of your object onto a platform. Then the platform moves down a fraction of a millimeter, and the nozzle draws the second layer directly on top of the first. It repeats this process hundreds or even thousands of times, fusing each new layer to the one below it, until your digital idea has become a solid physical object you can hold in your hand. The entire process boils down to 3 simple steps. First, you need the model. This is the digital blueprint, the 3D file of what you want to create. You can download these files from massive online libraries like Thingiverse or Printables, Or eventually, you can learn to design them yourself in free software. Second, you need a slicer. This is a piece of software that acts as a translator. It takes your 3D model and slices it into those hundreds of individual layers, and then it creates a set of GPS-like instructions called G-code that tells your printer exactly where to move, how fast to go, and how hot to be. It's the brain of the operation. And third, you print. You load these instructions onto your printer, press a button, and the machine takes over, building your object layer by glorious layer. Now, for a beginner in 2026, there are really only two types of printing technology you need to know about. And making the right choice here at the beginning is critical. On one side, you have what's called FDM, or fused deposition modeling. This is the hot glue gun method we've been talking about. It uses spools of solid plastic filament, which looks like a thick line from a weed whacker. The printer melts this plastic and draws with it. FDM printers are fantastic. They are typically cheaper, the parts they make are strong and durable, and the variety of materials is insane. You can print with plastics that are rigid, flexible, heat-resistant, and even infused with wood or carbon fiber. The downside is that you can often see the fine layer lines on the finished part. This is the workhorse technology. It's perfect for functional parts, prototypes, tools, and generally larger objects. On the other side, you have resin printing, often called SLA or DLP. Forget the hot glue gun, this is more like magic. It uses a vat of liquid, light-sensitive resin and a UV light source, like a high-resolution screen or a laser, to cure the liquid into a solid, one layer at a time. The results are breathtaking. Resin printers can produce objects with an absolutely insane level of detail, and a perfectly smooth surface finish that looks like it came from a factory mold. They are the go-to choice for things like intricate miniature figurines for tabletop games, jewelry design, or detailed character models. But there's a trade-off. The process is messy. The liquid resin is toxic, it smells, and you need to wear gloves and have good ventilation. After the print is done, you have to wash it in alcohol and then cure it under a UV lamp. The parts can also be more brittle, and the printers themselves have a smaller build area. So what's the verdict for a beginner? For 95% of people watching this, the answer is FDM. Hands down. It's safer, cleaner, cheaper, and far more versatile for the types of practical, problem-solving prints you'll want to start with. It is the perfect gateway into this world. Think of resin printing as your next step, a specialized tool you can explore once you've mastered the fundamentals of FDM. So we've busted the myth. We understand the basic concept, and we've decided that an FDM printer is our starting point. The journey from being paralyzed by confusion to being empowered by creativity has officially begun. In the next parts of this series, we're going to get our hands dirty. We're going to choose the absolute best beginner FDM printer for under $500, unbox it, and show you how to assemble it in under 30 minutes. We'll find our first model, prepare it in the slicer software, and together we will hit that print button for the very first time. But be warned, the single biggest mistake a new buyer makes isn't in the printing, it's in the buying. And in the very next video, I'm going to reveal the 3 most overrated features that manufacturers use to trick beginners into wasting hundreds of dollars on things they absolutely do not need. Your wallet will thank you. Alright, let's pull back the curtain on the first big marketing trap. Dual extrusion. You've seen it. The ads are mesmerizing. A printer with 2 nozzles gracefully dancing over the print bed, laying down 2 different colors at once. They show you a perfect, vibrant red and blue frog, or a complex mechanical part with a special, flexible material for the joints. The promise is intoxicating. Unlock a whole new world of multicolor, multi-material printing. It seems like the obvious upgrade, the feature that separates the toys from the serious machines. And for just $100 or $200 more, it feels like a no-brainer. Here's the reality they don't show you in that glossy ad. For a beginner, a dual extruder isn't a feature. It's a curse. It's arguably the fastest way to get so frustrated you quit the hobby entirely. Think about it. Learning to get one nozzle to print perfectly, at the right height, the right temperature, the right speed is already a significant challenge. Now, you're not just doubling the nozzles, you're multiplying the complexity by a factor of 10. First, you have to align them perfectly in 3-dimensional space. The X, Y, and Z offsets have to be calibrated to a fraction of a millimeter. If one nozzle is even a tiny bit lower than the other, it will drag across your print, ruining the surface finish and potentially knocking the entire part right off the bed. Then there's the ooze. While one nozzle is printing, the other one is just sitting there, hot and full of molten plastic. And what does hot plastic do? It drips. It oozes. So that inactive nozzle will inevitably drool a tiny bit of plastic onto your otherwise pristine print, creating ugly blobs and zits of the wrong color. Manufacturers have tried to solve this with U-shields and prime towers, extra structures printed on the side to wipe the nozzle clean. But this just adds more time and wastes a shocking amount of filament. You can end up using more plastic on the throwaway tower than on your actual model. It's a messy, wasteful, and deeply frustrating process that even experienced users struggle with. For a beginner, it's a nightmare. The smarter approach? If you dream of multicolor prints, start by printing separate, single-color parts and designing them to fit together. You'll learn about tolerances, design for assembly, and gluing techniques, skills that are 1,000 times more valuable in the long run than wrestling with a finicky dual extruder. The second overrated feature, and this one is even more tempting, is a massive build volume. The logic seems so simple: bigger is better. You see a printer with a build area the size of a microwave and you start imagining printing a full-size Iron Man helmet in one single piece. The marketing tells you, don't let your creativity be limited by size. They sell you the dream of giant monolithic prints. The problem is, they don't sell you the reality of what it takes to pull one off. A print that fills a huge build plate doesn't take hours, it takes days. We're talking 40, 60, even 100+ hours of non-stop printing. Now imagine you're 55 hours into a 60-hour print. You've used an entire 1 kilogram spool of filament, which costs about $25. You wake up in the morning, excited to see your masterpiece, only to find a giant tangled mess of plastic spaghetti. A tiny power flicker, a nozzle clog, a layer shifting by 0.5 millimeter overnight. Any number of small issues can cause a catastrophic failure. And just like that, 2.5 days of your life and a whole spool of plastic are in the trash. It is absolutely soul-crushing. Furthermore, a huge build plate is a liability. It takes significantly longer to heat up, uses more electricity, and is much harder to get perfectly level than a smaller one. The truth is, for your first year in 3D printing, 99% of the things you'll want to print will fit comfortably on a standard, medium-sized build plate, something around 220 by 220 millimeters. It's the industry standard for a reason. And for that one time you do want to print a giant sword or a piece of armor, you do what the pros do. You slice the model into smaller, more manageable pieces in your software. You print them separately, which is faster and far more reliable. Then you assemble them. This approach lets you orient each piece for maximum strength, and if one small piece fails, you only have to reprint that one part, not the entire thing. Don't pay a premium for a giant empty space you'll almost never use. And that brings us to the third and most deceptive overrated feature: astronomical print speeds. In the last couple of years, there has been a speed war in the 3D printing world. You'll see printers advertised with max speeds of 500 or 600 millimeters per second. Sounds incredible. The idea of finishing a 10-hour print in just 2 hours is the holy grail. But this is, without a doubt, the most misleading spec on the box. That max speed number is like the top speed of a supercar. A Bugatti might be able to hit 300 miles per hour, but you're only ever going to do that on a 9-mile straightaway in the desert with a special set of tires. You're not hitting 300 in the grocery store parking lot. 3D printing is all parking lots. It's constant stopping, starting, and changing direction. The printer almost never reaches its advertised max speed. The real factors that determine how fast you can actually print are acceleration and the Hotten's volumetric flow rate, basically how quickly it can melt plastic. A printer might be able to move its head at 600 millimeters per second, but if it can't accelerate and decelerate quickly, or if it can't melt plastic fast enough to keep up, that speed is purely theoretical. Trying to print at those top speeds with standard settings and materials will give you absolutely horrendous results. You'll see violent shaking, ugly ringing or ghosting artifacts in your print, corners that are rounded and bulging, and layers that are so weak they fall apart in your hands. A well-built, rigid printer that produces a beautiful, strong part at a consistent 150 millimeters per second is infinitely more valuable to a beginner than a wobbly, poorly tuned speed demon that produces garbage at a supposed 500. The goal of 3D printing is not to fail faster. It's to succeed reliably. So ignore the flashy speed numbers. They are marketing fluff, designed to make you think you're getting a next-generation machine when, in reality, you're often getting a machine that's just been pushed far beyond its quality limits. So, if we're ignoring the siren song of dual extruders, massive build volumes, and fantasy print speeds, what should we actually be looking for? It all comes down to what I call the beginner's triangle of success. These are the 3 pillars that will actually determine whether you love this hobby or abandon it in frustration. They are reliability, ease of use, and community support. Reliability is number one. You want a machine that is a dependable tool, not another project you have to fix. You want to be able to slice a model, send it to the printer, and have a high degree of confidence that you'll get a successful print on the other end. Ease of use is next. This means the printer shouldn't fight you every step of the way. It should have features that simplify the most difficult parts of the process, making it easier for you to get from an idea to a physical object. And finally, community support. Because let's be clear, things will go wrong. Your printer will clog. A print will fail. And when it does, you need to be able to type your exact problem into Google or YouTube and find thousands of other people who have already had that same problem and have documented the solution. A printer with a massive, active, and helpful community is one of the most valuable assets you can have. These three things, reliability, ease of use, and community support, are the foundation of a positive experience. They aren't as sexy as a multicolored chameleon, but they are what will keep you printing and learning for years to come. And out of all the features that contribute to this triangle, there is one that stands head and shoulders above the rest as the single most important innovation for beginners in the last decade. Getting this one feature right is the difference between a new passion and a $1,000 paperweight. In the next part, we are going to do a deep dive into the world of automatic bed leveling. I'll show you the one type you absolutely must have on your first printer, and the two older, cheaper versions that you need to avoid like the plague. Imagine you're building a house. What is the single most important step? It's the foundation. If that concrete slab isn't perfectly flat, perfectly level, it doesn't matter how straight the walls are or how perfect the roof is. The entire structure is compromised from the very beginning. Cracks will form, doors won't close right, and eventually you'll have a catastrophic failure. In 3D printing, the first layer is your foundation. It is everything. I cannot overstate this. 90% of all print failures can be traced back to a bad first layer. And the secret to a perfect first layer is a perfectly level print bed. This single task, getting the distance between the printer's nozzle and the build surface to be exactly the same at every single point, has been the number one source of frustration, of rage quitting, of printers being thrown in a closet to gather dust for the last decade. It is the single biggest point of failure for any new 3D printing enthusiast. For years we had to do this manually. It was a ritual, a dark art. You'd get a piece of standard office paper, and you'd move the nozzle to one corner of the bed. You'd slide the paper back and forth between the nozzle and the bed while turning a giant knob underneath that corner. You were looking for just the right amount of friction, a slight drag on the paper. Not too tight, not too loose. Then you'd move to the next corner and do it again. And the next. And the next. But here's the kicker. Adjusting the fourth corner would slightly change the first corner. So you had to go back and do it all over again. And again. And again. It was this maddening circle of adjustments we called tramming the bed. It could take 20 minutes, and even then, a slight temperature change in the room could throw it all off. This was the reality, and it was terrible. So, manufacturers started introducing something that sounded like a miracle: automatic bed leveling. The problem is, this term has been used to describe three very different technologies, two of which are obsolete traps for new buyers, and one of which is the key to your success. The first system you must avoid is what I call the deceiver. This was the earliest form of auto leveling. You'll see it on older or super budget printers. It involves a small probe that attaches near the nozzle, like the original BL touch sensors. The printer would use this probe to touch down on a few spots on the bed, usually the four corners in the center. It would then tell you on the screen, front left corner, minus 0.2 millimeters, back right corner, plus 0.15 millimeters. It gave you the measurements, but then you still had to turn the knobs yourself. It didn't automatically level anything. It just automated the measurement part. It was a glorified digital ruler. It's like a GPS that tells you you're lost but doesn't give you directions. It's not automatic, it's assisted manual leveling. And in 2026, it is an absolute waste of your time. If a printer's marketing says it has assisted leveling, or just shows a probe without explaining what it does next, run away. That brings us to the second system you need to avoid, which is far more common and far more sneaky. I call this one the crutch. This is a big step up from the deceiver, and for a while it was the industry standard. This system also uses a probe to touch down on the build plate, but instead of just 4 or 5 points, it measures a whole grid, maybe 16, 25, or even 100 different points. It uses this data to build a digital 3D map, or a mesh, of your bed surface. It knows every tiny hill and valley. Then when it starts printing, it uses software to dynamically move the Z-axis, the vertical axis, up and down ever so slightly to follow the contours of your uneven bed. If there's a low spot, the nozzle moves down. If there's a high spot, it moves up. It's essentially tracing the imperfections to ensure that first layer sticks evenly everywhere. It sounds amazing, right? It's a software solution to a hardware problem. But it's a crutch, not a cure. Here's the fatal flaw for a beginner. Mesh leveling systems only work if your bed is already mostly level. They can only compensate for minor imperfections, typically less than a millimeter of deviation across the entire surface. But when you're building your first printer, it's very easy to assemble it in a way that the bed is tilted by several millimeters. If you try to run this mesh system on a badly tilted bed, the software compensation just can't keep up. The nozzle will either dig into one side of the bed or be printing in midair on the other. So you, the beginner, are still forced to learn the dark art of manual tramming with the paper and the knobs to get it close enough for the automatic system to take over. It defeats the whole purpose of being a beginner-friendly feature. It helps, but it doesn't solve the core problem. It's putting a high-tech bandage on a broken arm. This brings us to the one system you absolutely must have on your first printer in 2026. This is the Holy Grail. This is what true automatic bed leveling looks like. I call it the game changer. This system isn't a crutch, it's a cure. It doesn't just map the bed and compensate in software. It physically fixes the problem. These printers use a high-precision probe, sometimes a strain gauge built right into the nozzle itself, to create that same detailed mesh map of the bed. But then, it does something magical. It uses that data to drive independent motors on the Z-axis to physically tilt the print gantry, or in some cases the bed itself, to be perfectly parallel with the bed's surface. Let me say that again. It doesn't just create a digital map of the errors. It eliminates the errors. It physically aligns the printer's mechanics to create a perfect foundation every single time you press print. There are no knobs to turn. There is no paper to slide. You don't have to get it close enough. The printer does the entire process from measurement to physical correction in about 90 seconds completely on its own. It is the single greatest quality of life improvement in consumer 3D printing history. This is the technology that takes 3D printing from a hobbyist tinkering project to a true home appliance. It's the difference between frustration and fascination. With this system, the bed leveling problem, the #1 killer of beginner enthusiasm, is simply gone. It's a solved problem. 5 years ago, this was a premium feature found only on printers costing thousands of dollars. Today, it is rapidly becoming the standard on entry-level machines. Any printer company launching a new model for beginners in 2026 without this level of true, hands-off, physically correcting auto-leveling is doing you a massive disservice. Do not give them your money. You will spend more time fighting with the machine than printing with it. When you're looking at a printer's feature list, you want to see phrases like fully automatic leveling, hands-free leveling, or independent Z-axis leveling. This is non-negotiable. So, now that we've guaranteed our printer can create a perfectly level foundation every single time, we need to talk about the ground that foundation is being built on. I'm talking about the build surface itself, that plate where your creations come to life. This is another area that has seen a revolution in technology, moving from painter's tape and glue sticks to advanced magnetic, flexible, and textured sheets. Choosing the right one is the difference between a print that pops off effortlessly with a gentle flex, and one that is either welded to the bed like concrete or slides around like it's on ice. So now that we have our foundation, let's look up. Let's look at the part of the printer that does all the magic, the part that's part high-tech glue gun, part robotic artist's brush. I'm talking about the print head, and more specifically, the hot end assembly. This is where solid plastic becomes a liquid dream. If the build plate is the canvas, the hot end is the pen, and understanding it is non-negotiable. At the very tip of this whole assembly, the part that literally touches your print is the nozzle. You might think it's just a tiny metal cone with a hole in it, and you'd be right, but that little cone is one of the most critical and easily swappable components on your entire machine. The vast majority of printers will come with a standard 0.4mm brass nozzle. Brass is a great starting point. It has excellent thermal conductivity, meaning it transfers heat to the filament efficiently, and it's inexpensive to manufacture. For printing standard materials like PLA, PETG, and ABS, a brass nozzle is your workhorse. But what happens when you want to print with something more exotic? Let's say you want to print a gear using a filament infused with carbon fiber, or something that glows in the dark. Those filaments are abrasive. The The tiny hard particles in them will act like liquid sandpaper on your soft brass nozzle. After just a few hours of printing, your 0.4mm hole could be worn out to 0.5, 0.6, or even larger, leading to sloppy, inaccurate prints. That's where hardened steel nozzles come in. They sacrifice a little bit of that perfect heat transfer, so you might need to bump up your printing temperature by 5 or 10 degrees, but they can handle these abrasive materials day in and day out without breaking a sweat. For the true performance enthusiast, you'll even find nozzles tipped with ruby or other exotic materials, offering incredible wear resistance. But for a beginner, knowing the difference between brass and hardened steel is the key takeaway. Then there's the size of the hole itself. That 0.4mm standard is the jack of all trades. It's a fantastic balance between detail and speed, but you can change it. If you wanted to print a highly detailed miniature figurine, you could swap to a 0.2mm nozzle. Your print times will increase dramatically, but the level of fine detail you can achieve will be absolutely stunning. On the flip side, if you want to print a large functional part like a storage bin, and you don't care about tiny details, you could install a 0.6, 0.8, or even a 1.0mm nozzle. You'll be laying down thick, fat lines of plastic, and a print that would have taken 12 hours might now only take 4. The trade-off is that you lose that fine resolution. It's like choosing between a fine point pen and a thick permanent marker. One is for detail, the other is for speed and strength. Now, moving up from the nozzle, we have the heater block. This is simply an aluminum block with 2 components screwed into it. A heater cartridge, which is a small ceramic rod that gets incredibly hot, and a thermistor, which is a tiny sensor that acts like a thermometer, constantly reporting the temperature back to the printer's mainboard. This creates a feedback loop, allowing the printer to maintain a precise temperature, say 210 degrees Celsius, within a single degree of variance. Screwed into the top of that heater block is one of the most ingenious and often misunderstood parts, the heat break. Its job is simple but absolutely vital. It allows heat to stay in the heater block where it belongs and prevents it from traveling upwards into the rest of the assembly. This is crucial. You only want the filament to melt right at the very end, just before it exits the nozzle. If heat creeps up the filament path, it can start to soften and melt the plastic too early, inside the cold end of the printer. When this happens, the softened plastic expands, gets sticky, and causes a catastrophic jam known as heat creep. It's one of the most frustrating failures for a beginner. A good heat break, often paired with a dedicated cooling fan blowing on fins just above it, is the unsung hero that prevents this nightmare scenario. So we have the nozzle to extrude, the heater block to melt, and the heat break to contain that heat. But how does the filament get there in the first place? That's the job of the extruder. This is the mechanism with a motor and a geared wheel that grips the filament and pushes it towards the hot end. And in the world of consumer 3D printing, there are 2 dominant design philosophies for where this extruder is placed: Bowden and direct drive. Let's start with Bowden. In a Bowden setup, the extruder motor is mounted on the printer's frame, away from the moving print head. It pushes the filament through a long flexible tube, usually made of PTFE, all the way to the hot end. Think of it like trying to push a string through a straw. The biggest advantage here is that the moving print head is incredibly lightweight. There's no heavy motor weighing it down. This means it has less mass and less inertia, so it can change direction very quickly without shaking the whole machine. This can lead to faster printing speeds with fewer vibration artifacts, which sometimes show up as a ghosting or ringing effect on the surface of your prints. The downsides? Well, that long tube introduces a bit of slack and springiness into the system. Controlling the exact pressure at the nozzle is harder. Retractions, where the filament is pulled back slightly to prevent oozing during travel moves, have to be longer and are less precise. And trying to print with soft, flexible filaments can be a nightmare. It's literally like trying to push a wet noodle through a drinking straw. It's just going to bunch up and jam. The alternative is direct drive. As the name implies, the extruder motor and drive mechanism are mounted directly on top of the hot end. The path from the drive gear to the nozzle is incredibly short, maybe only a centimeter or 2. This gives you immense control. Retractions are short, crisp, and precise, which dramatically reduces stringing and oozing. And because the filament is so well constrained, printing with flexible, rubber-like materials becomes not just possible but easy. The control is so direct and immediate. The trade-off, of course, is weight. You now have a relatively heavy motor moving back and forth, and all that extra mass and inertia can introduce more vibration into the system, potentially limiting your top speed before you see those ringing artifacts appear on your prints. For years, the debate has raged. Bowden for speed, direct drive for control and material compatibility. But as technology has improved, the lines have blurred. Lightweight pancake stepper motors and compact extruder designs have made direct drive systems lighter than ever, while advanced firmware features have made Bowden systems more precise. As a beginner in 2026, you'll find fantastic options in both categories. Many people start with the Bowden system for its simplicity and speed on standard materials, while others who know they want to experiment with flexibles might opt for a direct drive from the get-go. There is no single better answer. It's about understanding the trade-offs and how they align with what you want to create. So we have this incredible engine of creation. A precisely heated nozzle, a powerful extruder, and a perfectly level bed ready to receive the first layer. We've built the factory, we've tuned the assembly line. But we're missing the most important ingredient. We're missing the raw material itself, the very substance from which our ideas will be forged. And so we stand here in our newly built factory, with a perfectly tuned assembly line, ready to create. But a factory without raw materials is just an empty building. The substance we need, the lifeblood of this entire operation, is called filament. Think of it as the ink for your 3D printer, but instead of just black or cyan, this ink comes in hundreds of materials, each with its own unique personality, its own strengths and its own weaknesses. Choosing the right filament is like a chef choosing the right ingredients. You wouldn't make a delicate pastry with a tough cut of meat, and you wouldn't build a load-bearing bracket out of a material that shatters like glass. The material is everything. Now if you go online, you'll see a dizzying array of options. ABS, ASA, nylon, polycarbonate, carbon fiber infuse this glow-in-the-dark that. It's overwhelming. So let's cut through the noise. For a beginner in 2026, there are really only 3 materials you need to know about to start. Think of them as your starter pack. Master these, and you can print about 90% of anything you can imagine. First and most importantly is PLA. Polylactic acid. If 3D printing filaments were a neighborhood, PLA would be the friendly neighbor who brings you cookies, helps you with your lawn, and always has a smile. It is, without a doubt, the single best material to start with. Why? Because it wants you to succeed. PLA is incredibly forgiving. It prints at relatively low temperatures, it doesn't warp or peel off the bed easily, and it doesn't require any special hardware. Almost every single 3D printer on the market is designed to print PLA right out of the box. But here's the cool part. PLA is a bioplastic. It's typically derived from renewable resources like cornstarch or sugarcane. When it's printing, it doesn't have that nasty hot plastic smell some other materials do. Instead, it gives off a faint, slightly sweet smell, almost like waffles. It's the most pleasant printing experience you can have. And the sheer variety is staggering. You can get PLA in every color of the rainbow. You can get silk PLA that has an incredible glossy sheen. You can get matte PLA for a smooth, professional finish. There's even PLA infused with real wood fibers, so you can print objects that look, feel, and even smell like wood. You can sand them and stain them just like real wood. There's PLA infused with metal powders, which you can polish to a metallic shine. There's glow-in-the-dark, color-changing, and translucent PLA. It is the ultimate material for creativity. So, when should you use PLA? It's perfect for decorative objects, for figurines and characters, for rapid prototyping when you just need to check the size and shape of a part. It's strong, but it's also brittle. Think of it like a hard candy shell. It can take a lot of force, but when it fails, it tends to snap rather than bend. Its biggest weakness, its kryptonite, is heat. PLA has a very low glass transition temperature, which is a fancy way of saying it gets soft when it gets warm. If you print a phone holder out of PLA and leave it on your car dashboard on a sunny day, you'll come back to a sad, droopy puddle of plastic. So, for anything that needs to hold up to heat or serious physical stress, we need to level up. And that brings us to material number 2, PTG. If PLA is the friendly neighbor, PTG is its tougher, more dependable older sibling. PTG stands for polyethylene terephthalate glycol. That first part, PET, should sound familiar. It's the same family of plastic used to make water bottles. It's incredibly common. The G on the end is the magic ingredient. It's a glycol modification that makes the material stronger, more durable, and easier to print. PTG is the bridge between a hobbyist material and a true engineering-grade material. Its primary advantage is toughness. Where PLA snaps, PTG bends. It has a bit of flex to it, which allows it to absorb impacts and handle stress much more effectively. It also has significantly better temperature resistance. That phone holder that melted in the car? If you printed it in PETG, it would be perfectly fine. It's also more resistant to chemicals and UV light, making it a great choice for parts that might live outside or in a garage. So, you use PETG when you need a part to do something. Functional prints. A bracket to hold up a shelf. A replacement part for an appliance. An enclosure for an electronics project. These are the jobs for PETG. It shares many of the benefits of PLA. It's relatively easy to print and doesn't have a strong odor, but it does have a few quirks. It prints at a higher temperature, and it is notorious for something called stringing, where you get fine spiderweb-like strands of plastic all over your print. This is completely fixable with the right settings in your software, but it's something to be aware of. It's the small price you pay for a massive upgrade in strength and durability. Many people, once they get comfortable with PETG, find they use it for almost everything. Now for our third material. We've covered the friendly and easy, the strong and dependable, and now we need to talk about the flexible. This is TPU, or thermoplastic polyurethane. This isn't a hard plastic. It's a flexible, rubber-like material. If you've ever held a modern soft-touch phone case, you've probably felt TPU. Printing with TPU opens up an entirely new dimension of creation. Suddenly you can print things that are meant to be squished, stretched, and bent. You can print custom vibration dampeners for a drone, a super durable watch band, a flexible hinge that will never break, or even the soles for a pair of shoes. It is incredibly impact resistant because it just absorbs the energy. However, TPU is the challenge mode of our starter pack. I strongly recommend you don't make this your first, or even second material. Why? Imagine trying to push a wet noodle through a long straw. That's what it's like for your printer to push this soft, flexible filament through its extruder system. It can easily bunch up, kink, and cause a jam. It requires printing very, very slowly and with specific settings dialed in. Some printers handle it better than others, particularly those with a direct drive extruder, where the gears that push the filament are right next to the hot end. But it is absolutely a material you should aspire to master. Once you can print TPU, you've unlocked the ability to create a whole new class of objects that hard plastics simply can't replicate. So that's the big three: PLA for beauty and ease, PETG for strength and function, and TPU for flexibility and toughness. Of course, the rabbit hole goes deeper. There's ABS, the material Lego bricks are made of, which is very strong but notoriously difficult to print and releases unpleasant fumes. There are advanced materials like nylon and polycarbonate and carbon fiber composites for creating parts as strong as aluminum. But you can worry about those later. For now, your journey begins with one. So, how do you buy your first roll? My advice is simple. Start with a 1 kilogram spool of PLA from a reputable, well-reviewed brand. A 1 kilogram spool is the standard size and will last you for dozens and dozens of prints. Don't cheap out on the absolute bottom dollar, no-name filament. Saving $5 isn't worth the headache of dealing with a filament that has an inconsistent diameter or impurities, which will absolutely cause jams and failed prints. Stick to the brands people are talking about, and pick a simple neutral color like gray or white. It sounds boring, but these colors are the best for seeing the fine details and imperfections in your first prints, which will help you learn how to tune your machine perfectly. And my final, most critical piece of advice about material: keep it dry. Plastic filaments are hygroscopic, which is a science-wide word meaning they love to absorb moisture from the air. Wet filament is a death sentence for a good print. When the wet plastic hits the hot nozzle, the water inside instantly turns to steam, creating bubbles in your print. This results in a weak, brittle part with a terrible stringy surface finish. You'll even hear a little popping or crackling sound as it prints. The good news is, every new spool of filament comes vacuum sealed in a bag with a little packet of desiccant beads. When you're not using that roll, put it back in the bag, or in any airtight container with that desiccant packet. This simple act of discipline will save you from countless hours of frustration. We've done it. We have our factory, our assembly line is calibrated, and now we have our raw materials stacked and ready to go. We understand the essential properties that will bring our creations to life. We are so close, but we're still missing one final crucial piece of the puzzle. We have the physical world sorted, but we haven't touched the digital. We have the printer and the plastic, but we don't have the blueprint. We need the instructions that tell the machine layer by microscopic layer exactly what to build. We need the architect's plans. And those plans, in the world of 3D printing, come in the form of a digital file. The most common one you'll encounter is called an STL file, which stands for stereolithography. You don't need to remember that. Just know that an STL is the universal language for 3D shapes. It's a digital sculpture, a ghost in the machine waiting to be made real. So, the first big question is, where do you get these digital blueprints? Do you have to be a master 3D artist or a professional engineer to even get started? Absolutely not. You are stepping into an ecosystem that has been building for over a decade. Imagine a library, but instead of books, it contains the instructions to create nearly anything you can imagine. And the best part? Most of it is free. Welcome to the world of online 3D model repositories. These are websites that are the lifeblood of the maker community. The two giants you need to know about right away are Printables.com and Thingiverse. Thingiverse is the old guard, the original. It's a vast, sprawling archive with millions of models. If something can be 3D printed, a version of it probably exists somewhere in the depths of Thingiverse. It's an incredible resource, though sometimes it can feel a bit like treasure hunting in an old attic. Printables is the newer, more modern contender, and it's quickly become a community favorite. It's clean, fast, and has a fantastic feature. It rewards creators. People who upload popular models can earn points they can redeem for free filament or even new printers. This incentivizes quality and has fostered an incredibly active, helpful community. For a beginner in 2026, I would suggest starting your journey on Printables. Browse the trending models, check out the design contests. You will be blown away by the creativity on display. You'll find everything from replacement parts for your dishwasher, to intricate board game organizers, to beautiful artistic sculptures. You'll also come across sites like Cults 3D and My Mini Factory, which feature a mix of free and premium, paid models. This is where professional artists and designers often sell their highly detailed work. Think stunning tabletop miniatures or complex mechanical assemblies. Don't be afraid to spend a few dollars on a model you love. You're not just buying a file, you're supporting an artist and their craft. But for now, the free libraries will give you more to print than you'll have time for in a year. Just one word of caution: always check the license. Most models use Creative Commons licenses, which will tell you if you can use them for personal projects, if you're allowed to modify them, or if you can sell the prints you make. Respecting the creators is what keeps this whole amazing ecosystem thriving. So you've downloaded your first file. Maybe it's a simple keychain or a small figurine. You have the STL. But you can't just send that file to the printer. The printer doesn't understand shapes. It only understands commands. It needs a detailed step-by-step instruction manual. It needs to be told exactly where to move the nozzle, how fast to move it, how much plastic to push out, and what temperature to maintain. This is where the most important piece of software in your 3D printing toolbox comes in. It's called a slicer. The slicer is the magic translator. It takes your 3D model, the STL file, and it slices it into hundreds or even thousands of individual horizontal layers. Think of a CAT scan of your model. It then generates a new file called G-code, which is the actual instruction manual for your printer. G-code is just a long text file filled with coordinates and commands. A line of G-code might look something like G1X10Y25E0.5, which essentially tells the printer, move to coordinate X10, Y25, while extruding 0.5 millimeter of filament. It does this line by line, layer by layer, until your digital blueprint is a physical object. You have a few excellent and free choices for your slicer. The three main players are Ultimaker Cura, Prusa Slicer, and Bamboo Studio. Cura is one of the oldest and most widely used, known for its endless customization options. Prusa Slicer is famous for its user-friendly interface combined with powerful features. And Bamboo Studio, while newer, is praised for its streamlined workflow, especially if you're using a Bamboo lab printer. Honestly, for a beginner, any of these will work wonderfully. They all come with pre-made profiles for most popular printers. You'll literally select your printer model from a drop-down list, and it will load a whole set of tested, reliable settings to get you started. Your job isn't to understand every single one of the hundreds of settings. Your job is to understand the 4 or 5 that matter most. The first and most important setting is layer height. This determines the vertical resolution of your print. A smaller layer height, like 0.12 millimeters, means more thinner layers. This will give you a beautifully smooth, high-detail finish, but it will take a lot longer to print. A larger layer height, like 0.28 millimeters, means fewer, thicker layers. Your print will be much stronger and will finish much faster, but you'll be able to see the individual layer lines more clearly. For most prints, a value of 0.2 millimeters is the perfect balance of speed and quality. Second is infill. Your prints are rarely 100% solid plastic. That would be slow, expensive, and often unnecessary. Instead, the slicer creates a semi-hollow object with an internal support structure. That structure is the infill. You control two things: the percentage and the pattern. For most decorative objects, 15% to 20% infill is more than enough. For functional parts that need to be strong, you might bump it up to 40% or 50%. The pattern, like grid, honeycomb, or gyroid, can also affect strength and print time, but for now just stick with the default grid or cubic pattern. Third, and this one is crucial, is supports. Think about it. A 3D printer builds from the bottom up, layer by layer. It can't print in mid-air. If your model has a part that juts out at a steep angle, like a person's outstretched arm, it needs something underneath it to build upon. The slicer can automatically generate this scaffolding, which we call supports. These are thin breakaway structures that you'll snap off after the print is finished. Your slicer will have an option like Generate Supports, and you can set a threshold, typically for any overhang steeper than 45 or 50 degrees. Learning when and how to use supports is a key skill you'll develop over time. Finally, there's adhesion. The very first layer of your print is the most critical. If it doesn't stick properly to the build plate, the whole print is doomed to fail. To help with this, slicers have tools for bed adhesion. The two you'll see are a skirt and a brim. A skirt is a few loops of plastic drawn around the model without touching it. This is just to prime the nozzle and make sure the filament is flowing smoothly before it starts on the actual part. A brim is a single layer of plastic that extends outwards from the base of your model, like the brim of a hat. This gives your print a wider footprint, providing much more surface area to stick to the bed. For tall, thin objects or models with small, delicate contact points, a brim is your best friend. Layer height, infill, supports, and adhesion. Those are the big four. Master them and you're 80% of the way there. Your slicer will let you load a model, choose these settings, and then it will show you a full preview of the print. You can scrub through the layers, see exactly how it's going to be built, and it will give you a remarkably accurate estimate of how much filament it will use and how long it will take. This is the final step in the digital world. We started with an idea, found it as a 3D model file, and now we've used the slicer to translate it into a precise set of instructions, the G-code. We've bridged the gap between the concept and the command. We have the architect's plans, and we have the detailed, line-by-line instructions for the construction crew. All that's left is to hand those instructions over to the machine, prepare the job site, and press the button that brings it all to life. And that job site is your 3D printer. It's time to get our hands dirty. This is where the digital world of models and code collides with the physical world of heated plastic and moving parts. The first order of business? Loading our construction material. For most of us starting out, that means a spool of filament. Think of this as loading the ink into a pen, but 1,000 times more important. You'll typically find a small lever on the extruder, the part that feeds the filament. Pressing this lever releases the tension on the drive gears, allowing you to feed the filament through. Before you do, make sure the end of your filament is cut at a sharp 45-degree angle with the cutters that came with your printer. This isn't for looks. It creates a pointed tip that navigates the internal pathways much more easily, preventing jams before they even start. You'll push the filament in, and you'll feel it travel down a tube called a Bowden tube on many printers until it hits the hot end. Now you can't just shove it into a cold nozzle. You'll need to preheat your printer. On your printer screen, there will be an option to preheat for PLA, or whatever material you're using. Select it and wait for the nozzle to reach temperature, usually around 200 degrees Celsius. Once it's hot, you can push the filament that final inch. You'll feel a little resistance, then a give, and then you'll see beautiful molten plastic begin to curl out of the nozzle tip. That's the confirmation. You're loaded. If you're switching colors, you'll want to push enough through until the old color is completely gone and only the new one is extruding. With our material locked and loaded, we now turn to the single most critical element for a successful print: the foundation. I'm talking about the build plate. If the first layer of your print doesn't stick perfectly to this surface, the entire project is doomed. It will either warp, pulling up at the corners like a peeling sticker, or get knocked over by the nozzle mid-print, resulting in a catastrophic failure we affectionately call spaghetti. So, how do we prepare our foundation? First, it needs to be spotlessly clean. The oils from your fingerprints are enough to ruin adhesion. A quick wipe down with a microfiber cloth and some isopropyl alcohol, 90% or higher is ideal, will strip away any residue and give you a pristine surface. Do this before every single print. It takes 10 seconds and can save you hours of frustration. Next, we need to make sure the surface is actually sticky enough for molten plastic. Modern printers come with amazing build surfaces: textured PI sheets, glass beds, flexible magnetic plates that often work great on their own. But sometimes they need a little help. This is where a whole world of adhesion aids comes into play. The old-school tried-and-true method is a simple layer of blue painter's tape. Others swear by a thin layer of a washable glue stick or a light misting of extra strong hairspray. It sounds strange, I know, but these create a slightly tacky textured surface that the first layer of plastic can grab onto for dear life. You'll have to experiment to see what works best for your printer and your filament. Now for the big one, the single concept that separates beginners who give up in frustration from those who succeed. I'm talking about bed leveling, or as it's sometimes called, tramming. This isn't about getting your printer level with the floor using a bubble level. It's about making sure the nozzle is the exact same distance from the build plate at every single point. That distance is incomprehensibly small, about the thickness of a single sheet of office paper. If the nozzle is too high, the plastic will come out as a round bead, not sticking to the bed at all. It'll get dragged around, creating that dreaded spaghetti. If the nozzle is too low, it will scrape against the bed, preventing any plastic from coming out, and you might even damage your build surface. The sweet spot is where the nozzle is just low enough to gently squish the molten plastic onto the bed, creating a flat, well-adhered line. So how do we achieve this perfect gap? Many modern printers boast auto bed leveling, or ABL. They use a small probe to touch the bed in multiple spots and create a digital map of its surface. This is a game changer, but it's not a magic fix-it button. It compensates for tiny warps and imperfections in the bed, but it still relies on you to set the initial, overall distance. This is called the Z offset. You'll still need to fine-tune it, telling the printer to move just a hair closer or a hair further away to get that perfect squish. For printers without ABL, you'll do it manually. Don't worry, it's a rite of passage. You'll disable the motors, or use the menu to move the nozzle to each corner of the bed. At each corner, you'll slide a piece of paper between the nozzle and the bed while turning the adjustment knobs underneath. You're looking for a very specific feeling. The nozzle should scrape the paper just enough that you feel a slight drag, but not so much that it's difficult to move or tears the paper. You'll do this for all 4 corners and then the center. And then you'll do it again, and maybe a third time, because adjusting one corner can slightly affect the others. It takes patience, but when you master this, you've mastered the biggest hurdle in 3D printing. Okay, the filament is loaded. The bed is clean and prepped. The leveling is dialed in. Now we transfer the G-code, those instructions we made in the slicer, to the printer. The most reliable way is often the simplest. Copy the file onto an SD card or a USB stick, pop it into the printer, and select the file from the menu. Some printers can be connected directly to your computer with a USB cable, or even over Wi-Fi, which is incredibly convenient for sending files remotely. You've selected your file. You've taken a deep breath. You press print. And now we wait. But we don't walk away. Not yet. The first few minutes of a print are the most critical. The printer will spring to life. First, the bed will heat up to its target temperature, maybe 60 degrees Celsius for PLA. Then the nozzle will heat up to its 200 degrees. You'll hear the fans kick on. Then the printer will perform a homing sequence, moving its print head and bed to their 0 positions so it knows exactly where it is in space. And then it begins. The print head will move to the center of the bed and extrude a preliminary line of plastic along the side. This is called a purge line or a skirt. It's not part of your model. Its job is to prime the nozzle and get the plastic flowing smoothly before it starts on your actual object. And this line is your first best diagnostic tool. Watch it closely. Is it sticking well? Is it nicely squished and flat? Or is it round and loose? This is your last chance to make a tiny, live adjustment to your Z offset, nudging the nozzle a fraction of a millimeter closer or further away to perfect that first layer. Then the printer moves to start the model itself. The first layer goes down line by methodical line. This is the moment of truth. You are looking for perfection. Every line should be bonded perfectly to the one next to it, with no gaps. The whole layer should look like a single solid sheet of plastic, fused to the build plate. It should have a smooth, almost glossy appearance. This is your foundation and it needs to be flawless. If you see gaps between the lines, your nozzle is probably a little too high. If the plastic looks thin and transparent, or you hear a faint clicking sound from the extruder, your nozzle is too low and is struggling to push the plastic out. Don't be afraid to stop the print, clean the bed, and start over if that first layer isn't perfect. A bad foundation guarantees a failed building. But when it's right, it's a thing of beauty. Once you have 2 or 3 perfect layers down, you can finally breathe a little easier. The most dangerous part is over. The mesmerizing, almost hypnotic process of watching an object materialize from nothing is underway. But this is where the real learning begins. Because in 3D printing, even with a perfect start, things don't always go according to plan. Welcome to the club. Every single person who has ever owned a 3D printer has a collection of what we affectionately call failed prints. They are our badges of honor, our learning moments, our rite of passage. That first time you come back to check on a 10-hour print, only to find a chaotic nest of plastic spaghetti where your masterpiece should be. It's a feeling you never forget. But it's also your first great lesson. The spaghetti monster, as it's known, is almost always a symptom of one root cause. Your print lost its grip. It detached from the build plate. Once that first layer lets go, the nozzle has no foundation to build on, so it just squirts molten plastic into thin air, creating that modern art sculpture of failure. So, how do you defeat this monster? 90% of the time, the answer is bed adhesion. It all comes back to that crucial first layer we talked about. Your first line of defense is to re-level your bed. Even if you think it's perfect, check it again. A nozzle that's just a fraction of a millimeter too high won't press that first layer down firmly enough to get a solid bond. Your second weapon is a clean surface. The oils from your fingerprints, dust, or residue from previous prints can create a non-stick surface you absolutely do not want. A quick wipe with high percentage isopropyl alcohol before every print is one of the best habits you can develop. For stubborn prints, a wash with warm water and regular dish soap can work wonders, stripping away everything and giving you a pristine surface to work with. If you're still struggling, you can bring in adhesion aids. A thin layer from a simple glue stick or a light mist of extra strong hairspray can provide that extra tackiness your print needs to stay put. And in your slicer, consider adding a brim. A single layer of extra material around the base of your print that dramatically increases the surface area touching the bed, giving it much more to hold on to. You just peel it off when the print is done. But what if your print sticks at first, but then starts to peel up at the corners as it gets taller? This is another classic villain: warping. You'll see the edges of your print slowly curling upwards, lifting off the bed and often leading to a catastrophic failure later on. Warping isn't a problem of adhesion, but a problem of physics. Specifically, thermal contraction. As the hot plastic is extruded, it cools. And as it cools, it shrinks just a tiny bit. When you have a large, flat print, the upper layers cool and shrink faster than the base, which is being kept warm by the heated bed. This shrinking force literally pulls on the layers below it, creating an immense tension that can rip the corners right off the build plate. The number one tool against warping is a heated bed. Its entire job is to keep the bottom layers of your print warm and slightly soft, reducing that temperature difference and minimizing the shrinking effect. For materials like PLA, 60 degrees Celsius is usually the sweet spot. For more warp-prone materials like ABS, you'll need it much hotter. The second, and perhaps most effective, strategy is creating a stable environment with an enclosure. This can be as simple as a large cardboard box or a sophisticated acrylic case. By trapping the heat from the print bed, an enclosure keeps the air around the model warm, allowing the entire print to cool down much more slowly and uniformly. This drastically reduces the internal stresses that cause warping. Finally, just like with the spaghetti monster, a brim in your slicer settings can be a lifesaver, acting like little suction cups holding down the edges of your print against the forces of contraction. Now let's talk about a failure that looks truly bizarre. You come back to your print and it looks like it was hit by an earthquake halfway through. The top half is perfectly printed, but it's shifted a few millimeters to the left or right, completely misaligned with the bottom half. This is called layer shifting, and it's almost always a purely mechanical problem. Your printer's software has no idea this happened. It thinks it's still printing perfectly. The cause is that one of the motors, either for the x-axis, which moves the print head side to side, or the y-axis, which moves the bed forward and back, skipped a few steps. It was told to move 10 millimeters, but it only moved 9. Why would it do that? The most common culprit is belt tension. Your printer uses rubber belts to transfer motion from the motors to the moving parts. If a belt is too loose, it can slip on the motor's gear, like a bicycle chain skipping a tooth. If it's too tight, it can put too much strain on the motor, causing it to bind up and lose steps. Your belts should be tight enough to make a low bass-like twang when you pluck them, but not so tight they feel like a guitar string. The other major cause is a physical obstruction. The print head or bed could have snagged on something. A piece of plastic that curled up, a stray wire, or even the clips holding your build plate down. The motor tried to push past it, failed, skipped some steps, and then carried on as if nothing happened. Ensure all your axes move smoothly and freely by hand when the printer is off. If you feel any catching or resistance, you've found your problem. Okay, but what if the printer is moving perfectly but nothing is coming out of the nozzle? Or you hear a repetitive clicking or thumping sound coming from the extruder? My friend, you have a clog. This happens when something prevents the filament from flowing smoothly through the hot end. It could be a piece of debris, or it could be what's called heat creep. This is when the heat from the nozzle creeps up too far into the colder part of the hot end, melting the filament too early and causing it to swell and jam before it ever reaches the nozzle. That clicking sound is your extruder motor trying with all its might to push the filament through, but it can't, so it skips back. The first thing to try is a cold pull. Heat your nozzle up. Manually push some filament through to get it flowing, then set the temperature to cool down. For PLA, you'll want to let it cool to about 90 degrees Celsius. At this temperature, the filament inside the nozzle is solid enough to hold its shape but not so molten that it will break. Then, you yank the filament out from the top. If you're successful, it will pull the entire plug of semi-molten plastic out with it, hopefully bringing the clog and any debris along for the ride. You'll see a perfect impression of the inside of your nozzle at the tip of the filament. If that doesn't work, most printers come with a tiny acupuncture needle. With the nozzle heated, you can carefully insert this needle up from the bottom to try and dislodge the blockage. And if all else fails, remember this: nozzles are consumables. They are cheap and easy to replace. Don't spend hours fighting a stubborn clog when a 5-minute nozzle swap can get you back to printing. Finally, there's the aesthetic failure: stringing. Your print finishes, and it looks like it's been attacked by a tiny spider, with fine web-like hairs of plastic stretching between all the separate parts of your model. This is caused by plastic oozing out of the nozzle as it travels across an open space. The solution lies almost entirely in a slicer setting called retraction. When your printer is about to make a travel move, it can be told to quickly pull the filament backward just a little bit. This relieves the pressure in the nozzle and sucks the molten tip back up, preventing it from dribbling out. Dialing in your retraction distance and speed is key to clean, string-free prints. You can find retraction tower calibration models online that help you test many settings in a single print. Lowering your print temperature a few degrees can also help, as cooler plastic is less oozy. These failures aren't the end of the world. They are the curriculum. The spaghetti monster teaches you about adhesion. Warping teaches you about thermodynamics. Layer shifting teaches you about mechanics. And clogs teach you about the inner workings of your machine. By embracing and learning from each failure, you're not just fixing a problem, you're mastering the craft. And once you've mastered troubleshooting these common issues with your starter filament, a whole new universe of materials opens up. And each one comes with its own unique properties, its own challenges, and its own incredible possibilities. So let's step beyond that initial spool of PLA and explore the first tier of what's possible. Think of these next materials as the major players, the ones that form the foundation of functional 3D printing. First up is PTG. If PLA is the friendly, easygoing newcomer, PTG is its tougher, more dependable older sibling. The G stands for glycomodified, and that small change makes a world of difference. This is a close cousin to the same PET plastic used to make water bottles. It's significantly stronger than PLA, more durable, and has much better heat resistance. A PLA print might start to deform in a hot car on a summer day, but a PTG print will hold its shape. This makes it a fantastic choice for what we call functional prints, things that need to do a job. Think custom brackets for your workshop, a new housing for a Raspberry Pi project, or even a part for your drone that needs to withstand some vibration and impact. It also has a natural resistance to chemicals and moisture. Now, it's not without its quirks. P loves to be stringy, leaving fine, wispy hairs on your prints that you'll have to clean up. It also prints at a higher temperature than PLA, and it can be hygroscopic, which is a fancy way of saying it absorbs moisture from the air. If you leave a spool of PTG out for weeks in a humid environment, you might notice popping sounds during printing and a drop in quality. For this reason, many serious hobbyists invest in a simple filament dryer or an airtight container with desiccant packs. But once you dial in your settings, PTG becomes an absolute workhorse material you'll return to again and again. Next, we have the original champion of desktop 3D printing, ABS. Acrylonitrile butadiene styrene. You already know this material intimately. It's the same tough, durable plastic that Lego bricks are made from. For years, ABS was the gold standard. It's incredibly strong, has great impact resistance, and can withstand even higher temperatures than PTG, making it suitable for things like parts that will live inside your car's engine bay or custom fan shrouds for your printer's hot end. One of its most famous properties is its reaction to acetone. You can use acetone vapor in a controlled environment to smooth the surface of an ABS print, melting away the layer lines and leaving a beautiful glossy finish that looks almost identical to an injection-molded part. But ABS is demanding. It's the first material on our list that presents a real challenge. It has a nasty habit of warping, where the corners of the print lift off the bed as it cools. To combat this, a heated print bed is non-negotiable, and an enclosure around your printer is highly recommended to maintain a stable, warm ambient temperature. More importantly, when ABS melts, it releases fumes and volatile organic compounds, or VOCs. These can have a strong, unpleasant odor, and you absolutely need to print it in a well-ventilated area, not your bedroom or living room. For these reasons, many have moved to PTG or other modern alternatives for their daily printing. But for applications demanding that specific blend of strength, temperature resistance, and post-processing potential, ABS remains an undisputed king. And now for something completely different. TPU, or thermoplastic polyurethane. This is where 3D printing gets flexible. TPU is a rubber-like material that allows you to print objects that are squishy, bendable, and incredibly durable. Think of a custom phone case that's actually protective and soft to the touch, a flexible watch band designed perfectly for your wrist, or a custom-fit gasket to create a perfect seal. You can print vibration dampeners for your drone, or even the soles for a pair of prototype shoes. The possibilities are mind-boggling. Printing with it, however, requires a change in mindset. Imagine trying to push a wet noodle through a long tube. That's what printing TPU can be like. It requires much slower print speeds to avoid the filament kinking and jamming in your extruder. Printers with a direct drive extruder, where the motor that pushes the filament is mounted directly on the print head, tend to handle TPU much better than Bowden-style extruders, where the motor is mounted on the frame and pushes the filament through a long tube. It's a material that demands patience, but the first time you pull a print off the bed, and you can literally tie it in a knot, you'll realize you've unlocked a whole new dimension of making. Mastering these three PTG, ABS, and TPU will equip you to solve an enormous range of practical problems. But this is just the beginning. We're now entering the world of composites and exotic filaments, where materials are blended together to create properties that were once the exclusive domain of high-end industrial manufacturing. Have you ever wanted to print something that looks and feels like real wood? You can. Wood-filled PLA is a composite material that mixes fine wood dust into a PLA base. It prints just like PLA, but the finished object has a matte, fibrous appearance. And the best part? You can treat it like wood. You can sand it, stain it, and it even smells like freshly cut wood while it's printing. It's perfect for creating decorative pieces, architectural models, or anything you want to have a beautiful organic finish. What if you need something incredibly strong and rigid but also lightweight? Enter carbon fiber-filled filaments. These materials, often based in nylon or PETG, are infused with tiny chopped carbon fibers. The resulting prints are exceptionally stiff and strong, making them ideal for high-performance applications. Think load-bearing drone frames, RC car chassis parts, or functional prototypes that need to withstand serious mechanical stress. The one major caveat with these and other filled filaments is that they are highly abrasive. The hard particles, whether wood or carbon fiber, will act like sandpaper on your standard brass nozzle, wearing it out in just a few hours of printing. To print with these materials, you'll need to upgrade to a hardened steel or ruby-tipped nozzle that can withstand the abrasion. And of course, we can't forget the fun stuff. There are glow-in-the-dark filaments that absorb light and then radiate a ghostly green or blue hue in the dark. There are color-changing filaments that shift their hue based on temperature. There are even conductive filaments that can be used to print simple electronic circuits directly into your parts. Stepping into this world of materials fundamentally changes your relationship with your 3D printer. You stop thinking, what cool thing can I download and print? And you start asking, what problem can I solve? The material is no longer just a color choice. It becomes an engineering decision. Does this part need to bend? Does it need to survive a hot day? Does it need to be as light as possible? Does it need to look like it was carved from a block of oak? This evolution is part of the journey. As you venture into materials like ABS or carbon fiber nylon, you might find yourself needing to make small, accessible upgrades to your printer. You might install an all-metal hot end to safely reach higher temperatures. You'll swap in that hardened steel nozzle for abrasive materials. You might even build a simple, inexpensive enclosure out of foam board or acrylic sheets to help your ABS print stick. Don't see these as obstacles. See them as rites of passage. Each upgrade you perform, each new material you master, is a new superpower you are adding to your creative arsenal. You're not just a user of the technology anymore. You're becoming a true practitioner, tailoring your tool to match the boundless scope of your imagination. You're learning to choose the perfect substance to give your unique idea its perfect physical form. And with that understanding, you've unlocked the final, and perhaps most critical component of your 3D printing journey. It's not a piece of hardware you can buy or software you can download. It's the global interconnected community of creators, thinkers, and problem solvers you are now a part of. This is the ultimate upgrade. Because from this moment forward, you are never printing alone. For every failed print that leaves you scratching your head, there are 1,000 people on a forum or a Discord server who have seen that exact problem and have already figured out the solution. For every brilliant idea you have that seems just beyond your design skills, there's a creator out there who has shared a model that's 90% of the way there, waiting for you to remix it into something new. Think of sites like Printables, MakerWorld, and the classic Thingiverse not as simple file repositories, but as bustling digital workshops. They are living, breathing ecosystems of innovation. When you download a file, you're not just taking a design. You're receiving a piece of a person's creativity. And when you upload a photo of your successful print, you're completing that creative loop. You're giving feedback, showing appreciation, and inspiring the original designer and countless others to keep creating. This collaborative spirit is the engine that drives this entire movement forward. It's a culture of open-source generosity, where the default is to share, to help, and to celebrate each other's successes. So find your digital tribe, join the subreddit, lurk in the forums, see what people are making, ask questions, and most importantly, when you've learned something, share it. Pay it forward, because the collective knowledge of this community is infinitely more powerful than any single one of us. And as you become more integrated into this world, you'll start to see that this technology is so much more than a hobby. It's a powerful tool for practical problem solving. That broken plastic clip on your dishwasher door that the manufacturer doesn't sell anymore? You can model and print a replacement in an afternoon, saving an appliance from the landfill. That messy drawer full of batteries rolling around? You can design and print a custom, perfectly sized organizer that brings order to the chaos. This is the quiet revolution happening in homes around the world. A shift from being a passive consumer to an active creator of your own solutions. You stop asking, where can I buy one of those? And you start asking, how can I make one of those? This mindset shift is profoundly empowering. It turns everyday annoyances into creative challenges. This same power is fueling a new generation of entrepreneurs. We're seeing case studies of individuals starting businesses from their desktops, creating everything from custom cookie cutters for local bakeries to highly specialized jigs for other craftspeople. They're prototyping new inventions, test-fitting parts, and creating small batch production runs without the need for massive factory contracts or overseas manufacturing. This is localized, on-demand production in its infancy. For artists, it's a new canvas. They're creating intricate sculptures impossible to make by hand, fashioning wearable art, and blending digital design with traditional craft in breathtaking ways. The printer becomes a collaborator, a tireless assistant that can bring the most complex digital visions into physical reality. But perhaps the most impactful application is in the realm of accessibility. There are entire communities like the Enable Network, dedicated to designing and printing low-cost, open-source prosthetic hands and arms for people around the world. Innovators are designing and sharing models for free, custom-molded grips for pens for people with arthritis, braille learning tools for children, and tactile maps for the visually impaired. This isn't some far-off corporate initiative. This is happening right now in garages and spare bedrooms by people just like you. It's a stunning example of how this technology can be a force for good, directly addressing human needs in a way that mass production simply cannot. By sharing a simple design file, a person on one side of the planet can fundamentally improve the life of someone on the other. As we look toward 2026 and beyond, the pace of this evolution is only accelerating. The lines are blurring. The materials we talked about are just the beginning. We're on the cusp of a materials science explosion. Imagine printing objects with embedded electronic circuits using conductive filaments, or printing with flexible rubber-like materials that are also incredibly durable. We're seeing filaments infused with carbon fiber for parts as strong as aluminum, and biocompatible materials being explored for custom medical implants. The library of what's possible is expanding every single day. Simultaneously, the machines themselves are getting smarter and faster. The high-speed printing that is now becoming accessible was the stuff of science fiction just a few years ago. But the next step is intelligence. We're beginning to see the integration of artificial intelligence and machine learning. Printers that use cameras to watch the print in real time, detecting potential failures before they happen and automatically correcting them. Software that can take a simple text prompt and generate a complex, print-ready 3D model. Design optimization algorithms that can hollow out a part to use the least amount of material possible while maintaining maximum strength, mimicking the way nature designs things like bone. This all points to a much grander future, a concept known as distributed manufacturing. For a century, the model has been to build massive, centralized factories, produce millions of identical items, and then ship them all over the world. 3D printing flips that model on its head. It suggests a future where products aren't shipped, but data is. A design can be emailed to a local print hub, or even your home and fabricated on demand, where it's needed when it's needed. This means less waste, no need for massive warehouses of inventory, and infinite customization. It's a more sustainable, more efficient, and more personal way of making things. And that printer sitting on your desk? That's your personal gateway to that future. You are a pioneer on that new frontier. So, here we are, at the end of this guide, but at the very beginning of your journey. We've walked through the entire process, from the dizzying excitement of choosing your first printer, to the logic of the slicer, the feel of different materials, and the satisfaction of upgrading your machine. You now possess the foundational knowledge to not just operate a 3D printer, but to understand it. You speak the language of layers, infill, and supports. You see the world a little differently now. A broken bracket isn't a disaster. It's a design opportunity. An empty space isn't just an empty space. It's a place where a custom solution could live. You have the tools. You have the knowledge. You have a global community ready to support you. All that's left is the one ingredient that no guide or tutorial can ever give you. Your own unique curiosity, your own creativity, your own ideas. The single most important question is no longer how do I do it, but what will I create? Will you solve a nagging problem around your home? Will you design a gift for someone you love? An object that could only have come from you? Will you contribute a model to the community, helping someone you've never met? Will you explore the frontiers of art, business, or accessibility? The path is yours to forge. You are standing at the threshold of a world where if you can imagine it, you can hold it in your hand. So go. Power on your printer, heat up that nozzle, and make something that has never existed before. The digital blueprint is waiting. It's time to bring it to life.